Hello there. Today we are going to discuss some problems from almost the elementary problems in circular motion to all the way to more advanced problems. Okay, and we're going to try to learn to do these problems using polar coordinates. So this will be also an exercise for you to see how to use polar coordinates. So just to remind you what the polar coordinates are. So let's look at in polar coordinates, you start with your regular Cartesian coordinates. And so if you have a point here and you want to look at its position, so there's a particle there at some time t, then you use this distance r and this angle theta to denote the position, and that's actually sufficient. But if you want to write it as a vector, then you also have a unit vector, which we'll call it r hat. It does not have so this is a unit vector, and another unit vector which is 90 degrees to that. I'm going to call it theta hat. And these, if the particle is over here, the particle is over here, then the r hat in that direction will be r hat. So some theta 1 direction, r hat will be in that direction, and theta hat will be in that direction. So this r and theta hat direction depend on where the particle is. So going back to r and theta, so suppose this point is P, and its Cartesian coordinates is x, y, and its polar coordinates are theta. Then you have a following relation: x equals to r cosine theta, and y equals to r sine theta. And of course you can square and add, and r can be, you can see the r can only be from r to the infinity. R cannot be negative. So the r can be just take a positive square root of x square plus y square, and theta will go, you all the go pi and then all the way to 2 pi. So you think it's going to be 2 pi, but if object is moving around, so you can, theta can be actually minus infinity to infinity. So if you want to have how many cycles it has gone, that information that will be in the theta, right? So you can have theta kind of accumulate even beyond 2 pi, and the primary value of theta between 0 and 2 pi will be getting from the ratio of this. So this I assume you know this. And now the kinematics, when talking about the motion, first you should know how to describe the kinematics, right? So there are fundamental vectors. You have a position vector. This is position from with respect to O, and they have a velocity vector, and then you have an acceleration vector. You should know the formulas for these in whatever coordinates system you want to do. So for instance, in the Cartesian, you have r is xi hat plus yj hat. So this is like a vector way of writing, and the velocity vector is basically the time derivative of this, and this is a complicated stuff. And over here, if you go time derivative, so you get di hat dt, and dj hat dt will be 0, because these are constants. And so this you get a dx dt, I hat, dy dt, j hat. But rather than writing all this explicit way, we'll just write it. This is the way Newton wrote with a dot. So dot or prime you can use to denote one time derivative. Two time derivative will be two dots and things like that. Okay. Acceleration will be how this velocity vector changes with time, and we work this out. You can have a x double dot I hat plus y double dot j hat. Okay. If you're doing f equals ma, if you're in a Cartesian coordinate, you'll have a fx I hat plus fy j hat. It's staying in the two dimensions for the moment. Okay. In polar coordinate, you are going to in polar coordinate these vectors would be like r will be just r and r hat. Why? Because this is the r vector from here to here. That's the vector we're calling r vector, and it's this times the unit vector captures the direction, and you have but r hat, if you look at using theta and use a vector and divide by unit direction, so you basically r over r, and that's going to be x I hat plus yj hat over r, and we put x equal to r cosine theta and r sine theta, then this simply becomes cosine theta I hat plus sine theta j hat. And because theta hat is 90 degrees counterclockwise, right? Counterclockwise, going theta hat direction, then you can actually write down this should be minus sine theta I hat plus cosine theta j hat. And now the object moves, the theta changes, so r hat will also change with time. So when we do velocity vector dr dt, so this will simply be equal to two derivatives, dr dt r hat plus r dr hat dt. So you can see if I take a time derivative of this guy, this going to go into minus sine and this one cosine, so this will go into that, but then I'll get it if you have a dr hat dt, it will become theta hat d theta dt. So that's just from doing the derivatives. So if you don't understand how I got it, just try to do it, and explicitly you get that answer. Okay. So this will be basically writing in polar everything, r dot r hat, and this will be r theta dot theta hat plus theta dot theta hat. So we're going to use all of this when we solve problems. Okay, so I'm going to just lay out this thing for you so that it's a good review for you. dv dt. So now I'll have to plug this in, d dt r dot r hat plus d dt r theta dot theta hat. So this will require doing d theta hat dt. So if you do derivative of this, minus sine will go into minus cosine, and this cosine will minus sine. So I'm going to go to minus r hat. So this will give you minus r hat and d theta dt. So after all of this, you should check this, that it's going to be r double dot, so there will be something times r hat plus something times theta hat. So this is along r hat direction, this is along theta hat direction. So, and if you look at this derivative will give me theta hat direction, and this derivative will give me theta, so minus r theta dot square, that's come in here, and double dot here, r theta double dot will still be theta head direction. Then I'm going to have a 2 r dot theta dot in the theta head. This will give me one of them, and another will give me another. So that's going to 2. So this quantity here, is the radial. It's called radial. We can call it a sub r, and this quantity will come along the theta. So this is called radial acceleration, and this is called tangential acceleration. So if I'm over here, so acceleration pointed along this, if it's positive in that direction, it's negative in that direction, that's going to be AR, and along this, positive in that direction and negative in that direction, that's going to be a theta. So if you will see that this plays a very important role in some of the cases. Okay, so for the circular case, let's see what these guys will simplify in the case of circular. This is general. Circle will be r is moving on a circle, so r equals to some radius r constant. Then r is just r hat. V will simply become, you can see the r dot will be 0. R dot is 0, so this is going to be r theta dot theta hat. And acceleration will simply be, this will be 0, r dot is 0, that means r double dot is 0, so I'm going to get r theta dot is square r hat, as this is the centripetal acceleration. This is what we call centripetal acceleration, which is same as the radial acceleration, but towards the center, because this is negative, so it's going to be pointed towards the center. And this will be 0, r theta double dot theta hat. So this is the acceleration that we study when we study rotation, and this is the acceleration for something moving in a circle. And if it's moving at a constant theta, then this will be 0. If something is moving in a circular motion with a constant theta. Okay, so this is a review of this, and we're going to do some examples now. Okay, so here is a interesting problem. This comes from Klepner and Kolenko. So here's a wheel which rotates. This is at constant, and the bead, there's a bead that moves on the spoke as the wheel is rotating. So you might say bead was here, and then at t equal to 0, its velocity is pointed this way, but at this instant its velocity is pointed that way, and we're supposed to figure out which way the acceleration, velocity and acceleration is, and the magnitude. So we're supposed to figure out the entire velocity vector. Okay, this not bad problem. You can do it many different ways, but let's see what we have here. So what we're given is, if you look at these two coordinates for the bead, we're given that r of 0, this is time, is 0, and theta of 0 is, if something at the origin, then which way is pointed actually is, you don't know. So that will be indeterminate. What's also given is, as this r coordinate, bead only moves along the r coordinate, so we are given dr dt is u is constant, and of course the bead is going to move along the direction the spoke is actually going at the rate of theta, right? So that's another. So these are given. So we first write those things down. D theta dt is omega, and that's constant. That's also given. Okay. So from this other side, I wrote down what the position look like. Position look like this. Where so let's look at the position. Position vector will be r of t will simply be r of t, r hat of t. So this r hat is, of course, if I know the so r hat is cosine theta t I hat plus sine theta j hat. So if I know theta, I can know that, and then this r if I know from here. So clearly I can know both of these. From here I can know r up t equals to ut plus some constant, but using this gives me c equal to 0. So you can say 0 0 then c equal to 0. This one tells me theta t is equal to omega t plus some other constant c2. So at t equal to 0, theta is indeterminate, and we can take that to be 0. Let's see, infinitesimally say along the x-axis. So this is, I'm going to just pick one because it has a velocity direction along the x-axis. So although it's at the origin, at the very next instant it will be on some point along the x-axis. That's actually not completely correct, but I'm just going to assume it's if it's continuous function, then it can't just take off. So there will be, you can make a mathematical argument to show that it will be at theta. We can assign theta equals 0 for this purpose. So that will give me 0. So this will be theta t, and so this just turns out to be ut r hat, or ut you can write down cosine omega t I hat plus sine omega t j hat. Okay. Alright, so we got the position vector written out in polar coordinates, and then this is, you can say this is Cartesian coordinate. It looks more complicated and more simple, right? Okay, so now we want to the velocity t. We can of course take a time derivative of this over here, and or we can just say, all right, we are formula driven people, so I'm going to go over there, and there will be some r dot r hat, r theta dot theta hat. Let's start it that way. R dot r hat plus r theta dot theta hat. Suppose I do it that way, then which is nothing but coming from here. So r dot is just, this is r dot. R dot is u, so u r hat plus r, which is, we already figured out, r was ut. Theta dot, this is theta dot omega theta hat. So it looks very simple here, but of course for r hat I could write this, and for theta hat we could write down into I hat and j hat also, but we can just leave it in the polar coordinate. If you don't like to leave it in polar coordinate, or if it's maybe a problem requires you to do it in some other coordinate like Cartesian coordinate, then you have to write down u, and then you're going to have cosine omega t I hat plus sine omega t j hat coming from here, and from this will be plus omega ut theta will be minus sine omega t I hat plus cosine omega t j hat for theta hat. And they can combine I hat and j hat. This will go with that, this will go with that, and so we can have a full Cartesian version. How about acceleration? So acceleration, we don't have circular case, we just general case, because the radius has been changing in that problem. For instance, in this problem, it's the radius is changing, so r dot is not r is not constant, r dot is not 0. So here we'll go back to the full version here, and to do the full version we will see how far it goes. So a dot instant t is r double dot. Now if you look at this constant, the r double dot will be 0, so this will be 0 minus r theta dot square. Theta dot is omega square, so this will become omega square r hat plus r theta double dot plus 2 r dot theta dot theta hat. Make sure that this is, I didn't kind of made a mistake in copying, and that's what that is. Alright, so let's go back to the calculation page. Now this will be theta double dot. This is constant for this problem, so this goes to 0, and so this is u, and this is omega, and this is omega square. So we can write down as minus r omega square. R is u times t, so let's call it u times t minus u times t omega square r hat. So r hat is just for the direction, right? And this will be 2 times u times omega theta hat. So this is very simple, but if you try to write this in using a Cartesian, you'll have to kind of substitute all these big things here, and it's going to be a little bit like what happened to the velocity. It's going to be minus u or omega square. I don't like to write that. I like to write u omega square t, and r hat is just cosine omega t I hat plus sine omega t j hat, and then plus 2 u times omega minus sine omega t I hat plus cosine omega t j hat. So this I hat is not part of the argument. It's just because it's written next to it doesn't mean it's part of the argument. Okay, so that actually solves this problem that was supposed to write Bead's velocity and acceleration in any coordinate. So we're going to do another problem. Let's do a more standard problem. So there's a block tied to a string and it is going in a circle, and we're supposed to find the tension, the string, and it's going in the length of the string is r, which will be the radius of the circle in which the block will be moving. It may be moving in a vertical circle or horizontal circle or a little bit of cone type of shape, but we are going to, for the simplicity, we're going to ignore tension. Ignore gravity, force of gravity. You may imagine this is happening in outer space if you want. Okay, so let's do it in a polar coordinate. So this is my x and this is y, and so this is the instant t. Okay, so we always draw a picture of arbitrary instant. So if you look at it, known is r equals to constant, and this angle, this angle we can say theta t, and we can assume the theta at 0 was 0. Okay, it was here. Okay, so so these are known, and if you go in here in terms of the acceleration, not that part, but this, let's see if I have the right page here. Yep. So it's a circular motion case. So now we have, this is the case, right? So using that case, and if this is inertial frame, so we assume it's inertial frame, then in this frame, if you're going to be F equals to mass times acceleration, so this will be just like this got decomposed into a r hat plus a theta hat. This side can also replace fr r hat plus f theta, just like any vectors. So, and so we will get fr equals to mar and f theta equals to ma theta, and this is the word we can work with. So if we look at over here, which way are the unit vectors pointed? R hat pointed that way and theta hat pointed that way. So the only force is tension along the y, right? That tension is the only force that's along that y. So if you look at and tension is all along r hat direction. So T is r hat. If T is negative, then pointed towards O. If T is positive, then pointed away from O. Physically, we know tension will be pointed towards that, but the math will be consistent and work out fine. So, in terms of the acceleration, we already know that A sub r is r theta dot square, and A sub theta is r theta double dot. So if you look at, this is the theta, and if this thing is going at a constant v, then this distance covered this arc distance for constant speed on the circle, you get v times t. That's how much distance, the arc distance. That should be equal to r times theta. So you can see d theta dt is just v over r. So from here you can say minus r omega square, and omega square, and this is omega. So r omega square is r times v square over r square, and this is where the v square over r come from, right? So this is already some formula you might be familiar with. It's going to be minus v square over r. And how about this guy? So if you theta dot equals to v over r, which is constant, then theta double dot will be 0. So this is equal to 0. So there is no force in that direction. So what we get, T equals ma gives me Tr equals mar and 0 equal to 0. I get two things. 0 equal to 0. So Tr equals mr. So we already got that. This is minus m v square over r. So tension, therefore tension force on m is T equals to minus mv square over r hat. So this is the vector form of tension, which says it's direction wise negative will go with that. So the magnitude is mv square over r, and direction minus r hat. So the tension force is actually a function of time, right? Because although this is not changing, this is a function of time. So this thing changes so this is a function of time. So tension in this problem, if you look at certain time t is tension is pointed that way. So when the object is over there, tension is pointed that way. So their tension direction is changing, although the magnitude is same. So this tension is actually a variable tension. So whatever is applying responsible for tension, this agent which is over there, there is some post which is responsible for providing this tension, maybe a post which is attached to, then must apply force in different directions at different time. So it's not a constant force. It has a constant magnitude force, but varying in direction. Often you encounter problems where you can't don't ignore gravity. You can't ignore gravity. For instance, like a loop-to-loop airplane is going, or you're moving something in vertical circle. So gravity is pointing that way, and you're moving in a circle. So point of question is usually at this point, at this point, at this point. You might as well say at that point. So this is like these 4 points that people want to ask questions about. So let's see what we can do. So we can actually say this thing is going in this, And we can also say uh, it's going so that it's actually making a full circle. Suppose there's a car that's going on a vertical track, this toy car, and you might say, what speed has to have so it actually makes it over there? So it actually makes it over there, right? So let's make a concrete problem, okay? So here we are not going to assume the v not necessarily constant, okay? We're going to assume the problem say v maybe at this point it has a speed, say this is a time t, situation is over here, and v is v of some time t. So the speed is at this point v of t. Again, we want to know it's the same string, so this we want to know what's the tension T is going to be like. Mass is m. All right, and so looking at this, you can say, well, you know, the gravity is going to be this way. So this is x and y. So gravity is along the y-axis. But this thing is along the radial axis. So this problem could be handled in both ways. But the motion is a circular, right? So let's do it in polar. Which means I have to write the tension will be written as some tension r hat, but gravity, which is in this minus mg j hat. So I'll have to write this in terms of r hat and theta hat, right? So we can do it a couple of different ways. You can do it geometry wise, this is angle theta, or you can do algebra wise. So remember that r hat was cosine theta I hat plus sine theta j hat, right? And theta hat was minus sine theta I hat plus cosine theta j hat. And from there I could if I multiply this with sine theta and multiply this with cosine theta and added them, I'll get rid of I hat. So this will become sine square theta, from cosine theta you get j hat, and the other side will be sine theta r hat plus cosine theta theta hat. So this actually turns out to be minus mg sine theta r hat minus mg cosine theta theta hat. So now if you look at the net force, so net force in F equals ma, if you look at this force is nothing but T plus Fg, and this will be just total tension. If you say this, I want T to be positive, then tension is that way, so this will be minus, I can put that like that just to save time later, okay? So this minus T minus mg sine theta r hat minus mg cosine theta theta hat. And on the other side, because this is going in a circle, we already know what to expect. So that's going to be minus for MA, this side is going to be minus mv square over r, and this is function of time. So maybe just leave it like that, minus mr theta dot square r hat plus r theta dot theta and m r theta. So that's, you can see that equal to that and this equal to that. So you can write down what the tension will be. So minus t minus mg sine theta equals to mr theta dot square and minus mg cosine theta will equal to mr theta double dot. Now, rather than the problem in our problem earlier, in the problem statement was I had given the speed at that point is v of t. So I want to write down into the v of t. So if you go look into our velocity vector, velocity vector is at time t is r dot time t r hat plus r theta dot theta hat. So at that instant you can see that this is 0 here because radius is not changing, and so this is v, this is what the v is in this situation. The v is how fast it's going in that direction, so that's the speed, so that's the v. So if I have r theta dot equals to v, and this r is the radius, so theta dot is v of r in this case. So this is v of t square over r square, and this r cancels on this, and so this is mv square over r, and so theta is, it tells me where it is at this instant. It was an angle theta. So in order to figure out theta completely, I have to solve this second equation. So I have two equations. So solve one, which is very hard to solve, okay, to get theta of t from theta dot of 0 and theta of 0 is just equal to 0. So given this and this is a differential equation you can solve for theta of t. It's a second, and then you, solve two, plug in 1 to get t equals to, this comes on the other side, m v square t over r minus mg sine theta t. Okay, so actually I'm looking at it. Our original problem was to be able to say something about, like A, B, C, D, these points. Those are easy points. So even if you don't solve this, you can use this to tell tension at different points. So you can say when a tension and A will be when theta is 0, so this will be mv square at A times r. When it's B, when it's the top of the trajectory, tension at B, tension B will be, theta will be, this will be 1, so this will be mv square over r minus mg, and tension C will be mv square c r, and tension when it's D, this becomes a plus. But you can see right here there's going to be a problem. This, we already said this has to be positive. See, we already took into account the tension is pointed towards the center because it's not pushing this block away from the center, so it's the tension in the string pulls in. So based on that, we can say that there has to be at the very top, so this is the top of the trajectory, at the top this can't be negative. So we have to have velocity sufficient to make it through the circle. That information is already here. So mvb square over r has to be greater than or equal to mg. So the speed over there has to be at least this much. So that means cancelling out m, and if this is the speed, so it's going to be positive, must be greater than a square root of gr. Okay. There is another really classic problem. So here is a drum, and it can rotate, and you spin till you become reach a certain spinning rate, let's call it omega, and then the bottom falls off. So there's no bottom, and so if a person is standing here, there is no normal force, and this person actually keeps spinning in a circle without being supported below. So the question is, what is the rate? So a couple of things we need to know is there. If you look at just the vertical direction, you have a gravity, and if there is no vertical force here, then the person will certainly just slide, accelerate it. So there is no normal from the floor because the floor fell off. Then there has to be some kind of static friction to it's not sliding, so it's some kind of static friction that has to be there. Well, so if you look at from in terms of axis, this is the z-axis, and let's call it let's call it x-axis, y-axis, and this is at some theta. So this is the radial axis at that point, and theta hat is that way. So it turns out to be we can have things written down in r hat, theta hat, and k hat. So if we write down F equals ma, in these it will look like Fr equals to mar, F theta equals to ma theta, and Fz equal maz, component wise. Okay, now it's going in a circle of radius r, so this is radius r. Then this we are going to have a equals to minus omega r omega square r hat plus 2 times theta dot r d omega dt So this theta double dot, theta hat. Now at this instant omega remains, so omega reaches final, kept fixed, so this will be 0. So we have n plus 0 k hat. So this will be a. So if I look at it in terms of Newton's equation, in the radial direction there has to be a force, because this the acceleration which is pointed in that direction with a negative. R hat is pointed away from this center, so we have to have a force, and if you look at it, there's only force can be from the drum, so that force has to be there, and we just call it normal. So there's a normal from the floor, and this is a normal from the side, and is pointed towards the origin. So if I look at F, it is a normal from the, so R hat direction is that, there's nothing along the theta direction, and the k hat direction is Fs minus W k hat direction. So now when I use F equals ma, it's really trivial at this point. So the normal force would be mr omega square, and using the velocity thing, that will be mv square over r. So here omega times r is the speed, as we saw in the previous example. So this is for the normal force, and the other thing we find is the static friction has to be equal to W. There has to be that much static friction. If you don't have that much static friction, then it's not stable. So suppose you had a mu s, which will be given. So this mu s is based on the maximum static friction. So Fs max times Ns will be the, and so the minimum mu s that you will need, so writing this mu s, suppose I had needed max, just assuming using that will be mu s Fs divide by mu s both sides, then divide by mu s both sides, then I'm going to this will become ns. So mv square over r will have to be mg over mu s, and you can see it completely independent of who the rider is. The mass got cancelled out. So the mu s, you can see mu s has to be equal to, at least it has to be greater than this, otherwise it's not going to be stable. Mu s has to be equal to, gr over v square. Let me make sure I got this right. So mu s v square over r equal to g, and then gr over v. So sometimes people ask this question about what kind of mu s you will need for the system to be stable. So you want to provide enough static friction so that you don't have to use the maximum. You can go up to that, right? So you actual f, so actual fs is mg, and this fs lies between 0 and fs max. So as long as you've got sufficient, if you got this kind of mu s, then you have a sufficient mu s. If it's less than this mu s, then you're not providing sufficient mu s. Okay, I think I'm going to stop here, and process this video, see how it came out. So I'm working with a new set now, while I like to write on a piece of paper and pen, because in the future I'm building up to do some more advanced physics concepts, which maybe better explain by actually writing on a piece of paper. Okay, talk later, bye.